Okay, welcome back to algorithms. Today we're going to be talking about two really important classes of problems and a little bit about the relationship between them. And these classes are called P and NP. So it's very likely you've run into these before in some context. And I've mentioned them very briefly at various times throughout the semester. But today we're going to start to really get into the formal and important definitions of these. To start though, let's just take one backward glance at sorting. So last time we identified this fact about sorting algorithms, that if they depend on element comparisons, they must run in at least n log n time. So we can express this in terms of a Venn diagram. And so I'm going to write this as a Venn diagram of problems, or of classes of problems. So this inside circle here is the set of all problems that can be solved in linear time. Okay, so solved, let me call it solvable in linear time. Okay, and I'm not calling this time of n. So for those of you who've run into some CS theory concepts before, this isn't time of n because I'm not restricting to decision problems. So just, if you don't understand what I just said, don't worry about it. But if you do, that's what's happening here. So this inner circle is the set of problems that are solvable in big theta of n time. And then this bigger circle is the set of problems that are solvable in n log n time. Okay, solvable in n log n time. And so what we identified was that comparison-based sorting is here. Right, so that is sorting without priors on the inputs, right? Sorting where we don't know anything about the inputs. So I'm just going to call that sorting, right? So I'm not fiddling with the distinctions between like problems that we can solve using counting sort versus the ones we require something like merge sort. I'm just saying here these are the problems that that we can't do with counting sort. So here's I'll just call it sorting. Okay, so sorting lives in here, right? Sorting cannot be solved in linear time, but it can be solved in n log n time. So this is one way of expressing that fact. So there's another thing that we ought to notice about sorting, and that's that if I give you an array, and I say don't bother sorting it, just tell me whether it's sorted. We could ask how long does that take, and it's not too difficult to see that it would take linear time to identify whether or not the array is sorted. Okay, so we could think about sorting as a problem that we can only solve the problems completely in n log n time. But if all we want to do is verify correct solutions, we can do that in linear time. And so we can kind of express that using a different Venn diagram. So here's one Venn diagram, but then another one would look something like this. Here's the problems that can be verified in linear time. Okay, so this is the set of problems. Let me call this verifiable. So the set of problems whose correct solutions can be checked, can be verified to be correct in linear time. So verifiable in theta of n time. Okay, and this need not be the same as this set, right? Those two may not be equal, right? The big set on the top and the big set on the bottom. These are two completely different Venn diagrams. But then I can also put a subset in here that is exactly this subset up in the top one. So these are the problems that are solvable in linear time. Okay, so these two sets, the inner sets are the same. Those are the same, whereas these two are not the same. Right, and I'll say not necessarily the same. Okay, and so notice that it's the inclusion in the bottom Venn diagram has to be this way. Right? If I have a problem that I can solve in linear time, in other words, if I have a problem that is in here, in this inner set, then the fact that I can solve it in linear time necessarily means that I can verify its correct solutions in linear time. Okay, so let me write that down. That's quite important, and that'll come back again and again in this part of the course. So if a problem is solvable in linear time, then it is necessarily verifiable in linear time. In other words, if I give you a correct solution and I ask, is this solution correct? What you could do is you could just say, well, let's just throw that away and just check, right? And just go solve the problem up front and say, yep, sure enough, this problem is the way is what you were asking for. So if the problem is solvable in big theta of n time, it is necessarily verifiable in linear time. Okay, or I'm abbreviating a bit here. Okay, so what does this do? Well, this suggests. I mean, it doesn't just suggest. This illustrates that there are problems that are easy to solve, or that are easier to verify than they are to solve, right? Because what do we know about this? We know that sorting lives here, right? Sorting cannot be solved in linear time, but it can be verified in linear time. So there's this asymmetry with sorting in terms of which direction you're trying to go. If you're trying to start at the correct solution and check that it's correct, that's fast. If you're trying to start at an unknown solution and generate a correct solution, or something like that, that's a little bit harder. Not much harder, just logarithmically harder, but it's a little bit harder. So these two problems, or this one problem, sorting, essentially has an asymmetry depending on whether you're trying to solve from scratch or trying to verify a solved solution. So this doesn't seem too surprising, but it turns out that a question very similar to that is at the heart of one of the most important areas of study in theoretical computer science.